and we're looking at the derivative of a function, so 3.1. And so we're going to start with what is the definition of a derivative. So I'm going to do a visual explanation of this. So let's start with a graph, and this may be familiar to you. And I'm going to draw a curve, and this curve is a function. This would be really great if you guys could actually teach this. This shows real understanding of what the derivative is. Derivative means instantaneous rate of change, okay? So if I look at this graph, and I'm going to examine a section of this graph from A to B, okay, and this probably is looking familiar to you. If I examine a section of this graph from A to B, I can find the rate of change, and the rate of change is the slope of the secant line. Matter of fact, we could say that this is the average rate of change, okay? So that's our secant line, and we all know the rate of change for the secant line, the slope of the secant line is the average rate of change from A to B, and it's f of B minus f of A over B minus A. Now, what I want to do is, what if that secant line started to become closer to a tangent line? So in other words, what if we took B, I'm going to grab B, and we moved it. Let's see if I can move just B, it's going to disappear. What if I move B over closer, like that? That's going to change my secant line, right? My secant line is going to get, smaller, right? What if I move B yet again, even closer, let me grab B, it's going to disappear. You can't see it while I'm moving it, but now B is even closer, right? And my secant line is, that's not very good. Let me do a better secant line. So here's my secant line, right? Now, it's starting to get closer to looking like a tangent line. A tangent line is a line that touches the curve just at one point, at the point of tangency, okay? So what I'm going to do is I want B to get super close to A, almost on top of A, but just a tiny bit away. And so let's just zoom in on this. And as a matter of fact, I'm going to do the following. I'm going to say, instead of going from A to B, I want to go from X to some new value, and that new value is going to be X plus H, where H is the distance between my A and B. Okay, so my A point is X, and my B point is X plus H. Okay? Now, and so what is the slope of this this secant line now? Now the secant line, let me do that in green, would be right here, right? Now, of course, as H gets really, really tiny, this secant line is actually going to end up becoming the tangent line, right? That's what's going on, right? That happens when H is really, really close. You see that? Okay, so for visual purposes, though, I'm going to leave H so that it's not totally on top of, totally disappears, so we can see it. We can see H as a distance. But H is actually going to 0, but not quite at 0. It becomes a limit. So what happens to my slope of my secant line? Remember, the slope of the secant line equation was f of B minus f of A over B minus A. Okay, this was the slope of the secant line. Now, if I rewrite this with X plus H and X, this slope of this secant line becomes f of x plus h, because that's the b, minus f of x over b minus a, or our b is x plus h, and our a is x. And of course, what happens? The x's cancel out. And all I have on the bottom is h. Okay? So this is the slope of the secant line when a is x and b is x plus some h value. Okay? And this also is an important, and we've seen this before, because this quotient has a name, and it is called the difference quotient. So this is, let's write this name because this is an important name in calculus. You've seen it in pre-calculus. It's called the difference quotient. And so I'm going to do a little arrow pointing to what I've highlighted. That is the difference quotient. So the difference quotient, in fact, is the slope of the secant line. However, we use the difference quotient to find the slope of the tangent line, because what happens is, as h goes to 0, we end up finding, let's draw our tangent line, I'll draw that in black. We end up finding, here's our tangent line. There, this is the tangent line here. And so if this is the tangent line, getting this sort of small, then the slope of the tangent line is equal to the limit as h goes to 0, starts to go away, of the difference quotient. This is the slope of the tangent line. Now if you think of, let me get rid of this right here, let's move some of this away so it doesn't get too confusing. If you think of the secant, the slope of the secant as the average rate of change, the slope of the tangent is the instantaneous rate of change. Okay? So the slope of the tangent is the instantaneous rate of change of a function of f of x. And the instantaneous rate of change of a function is called the derivative. That is to say that the limit as h goes to 0 of the difference quotient is the definition of the derivative. So I'm going to grab this, let me copy this, and I'm going to open up another page. Paste this down. And this is what we call the derivative. The derivative of a function. It is the limit as h goes to 0 of the difference quotient. And the way we write derivative is we say f prime of x. That's how we write the derivative. And so I can say that f prime of x is equal to the limit as h goes to 0 of the difference quotient. There are a couple other ways to specify the derivative. You may see it written as f prime of x, that's the derivative. Or we say the derivative with respect to x of f of x, that's another way to write the derivative. Or you may see the derivative of f of x with respect to x, or you will see dy dx, and these all mean derivative. But the key thing to get from this, and I just wanted you to be able to recognize it when you're asked for the derivative, is this, that the definition of the derivative is the limit as h goes to 0 of the difference quotient, and it represents the instantaneous rate of change of a function.